This is a recap of classwork we did on Friday for those of you who missed it or those of you who want to see it again. We're not going to go too much further with this just for lack of time, but we were graphing a couple of funky polar equations and discovering that they actually had some interesting answers to them. The first one was r equals 8 divided by 2 plus sine theta. It looks like it should be more complicated than the one I did in the other example because of the division, but it actually turns out to be quite a bit nicer in some ways. So let's just fill out a table of values. I suggested just doing 0, pi over 4, pi over 2, 3 pi over 4, not all the special values, although that would be good practice. So sine of 0 is 0, sine pi over 4 is root 2 over 2, sine of pi over 2 is 1, and then basically we get just these numbers. Again, the sine of 3 pi over 4 is root 2 over 2 again, sine of pi is 0. Now we get minus root 2 over 2, minus 1, again minus root 2 over 2, and back to 0. Definitely stuff that's good to review because we're going to be using sine and cosine a fair bit in these last weeks. Then we're just going to plug that into the 8 over 2 plus sine theta thing. So that's a little laborious, and we need the calculator to get a sensible value, but it's not too bad. Clearly the first one is 4. 8 over 2 is 4. The next one turns out to be about 2.96. The next one's not hard. It's 8/3, or 2.67. The next one is the 2.96 again. Notice that if these numbers are the same, these numbers are going to be the same. So there's going to be a symmetry here. This is up and to the right. This is up and to the left. We're going to discover there's a symmetry around the y-axis. We'll see the whole picture in a minute. Pi, we're back to 4. Here, it's going to be a bit different. Here, we got 2 minus root 2 over 2. This becomes rather small in the denominator, and so the whole thing gets bigger. About 6.2. No, 6.19, I guess, to keep 3 sig figs there. And finally, at the bottom, 3 pi over 2, we're going to get 8. 2 minus 1, so the whole thing is 8. Now back to 6.19 symmetrically, and then back to where we started at 4. So if we plot those points, I'm not going to do it point by point plotting here. Let's bring this guy up. Ooh, not that much. Okay, let's bring this guy up. And we've got a very nice graph. Now it's hard to we discovered it's actually hard to get a really good looking graph out of this because of just how you draw things by hand. But it starts out, remember this is the same scale I've been using before, 2, 4, 6, 8. Starts out at 4. Then at the 45-degree position it's about 3, halfway in between the 2 and the 4 ring. Then it's down to about 2 2/3, so inside the 3 ring. Then back to 3, back to 4, then out to a little more than 6, past the 6 ring, out to 8, and then 6, and then back to 4. And it's hard to get this to look really pretty, as I said, but it looks, if we let the computer graph it, it looks a whole lot like an ellipse. And it even kind of looks like the origin of coordinates is one of the foci, and both of those statements are true. And we'll be able to prove that in a second. So that's very cool that this seemingly complicated graph gives you an ellipse. Well, now we're just going to change it just slightly. It was 2 plus 1 sine theta on the bottom. Now let's just make it 2 plus 4 sine theta. Seems like a slight change, but in some ways it's actually pretty drastic. We'll see in a second what's so drastic about it. I suggested that people do a different spectrum of values here, 0 to pi, but all the simple values first. And I'm going to leave some space on the ends for my own devious reasons. So here, let's just put in the sine values. It's 0, 1/2, root 2 over 2. Let's make that a nice fraction. And then root 3 over 2. Oh, whoops, I forgot a pi over 3. That's easy to fix. Oh, except I put it in the wrong place. Okay, so pi over 3, there we go. Pi over 2. Okay, this is 1. 2 pi over 3 is back to root 3 over 2. Then this is back to root 2 over 2. This is back to 1/2. And sine of pi is 0. So when we put those values in, again, I pre-calculated them. It turns out to give us, well, 4 to start with, same deal, 8 over 2 plus 0. Then when sine theta is 1/2, then that's 2 plus 2. Oh, it's 2. That's a nice, easy value. Okay, 8 over 2 plus 2. Then it gets a little bit messier. It's 1.66, and then 1.46, and then 1.33, when this is up to 1, it's 8/6 or 4/3. Okay. Then it starts getting bigger again symmetrically. And back to 2, and then back to 4. Okay. So we can graph those. But what's interesting about that graph is that it doesn't close up on itself because we haven't gone all the way around. Well, what if we went further around? What if we did, it'd be very natural, to go up to like 7π/6, and I'm going to leave a space in between, again, for my devious reasons. Here, we get a real rude surprise. The sign of 7π/6 is -1/2. 4 times -1/2 is -2. 2 minus 2 is 0. Uh-oh, this is DNE. That does not exist. And why does it not exist? Because the denominator is getting too small. That would suggest that what's happening is the whole thing. Oh, I didn't put the r equals in here. The whole thing, the r equals, the radius is getting too big. It might be going to infinity. So maybe the question is, does the radius go to infinity? Well, let's see what happens if we go like halfway in between. Halfway in between here, it's 13π/12. Because this is 12π/12, that's 14π/12. Here's 13π/12. The sign of that is, oh, let's do that. I forgot to do that ahead of time. 13π/12. That's definitely one you need the calculator for. I wouldn't expect you to know that one. Minus 0.26. Minus 0.26. I did pre-calculate this one. It turns out to be 8.29. So it's getting bigger. And as this number changes from 0 to minus 0.26 to minus 1/2, this denominator is going to get smaller. The whole thing's going to get bigger. So yes, the radius will go to infinity as the angle approaches 7π/6. 7π/6. Similarly, if I went backwards to -π/6, going to have the same problem. -1/2, that's going to be DNE. Does not exist. And if I went halfway in between, this is what I had people do, -π/12, symmetrically it's the same number, and the same number here, 8.29. And so as the angle approaches 7π/6 or -π/6. Interesting. Let me clear off that scratch work here. So what does it look like? Well, I pre-plotted it because I wanted it to be quick on the video here. It starts out at 4. See, if we're starting at 0, let's ignore these tails for a minute. We started out at radius 4, then it went immediately to radius 2, and then down to like 1 1/3, and then symmetrically up to 2, up to 4. And then we discovered if we extended it to, if we tried to extend it to this line, this is the 7π/6 line, it was going so far out that it wasn't even meaningful. When we went to the 13π/12, which is right here, these little guys are 12s. 13π/12, we got something just beyond the 8 ring. Remember, this is 2, 4, 6, 8. I forgot to put the scale on. And so it's getting pretty far out there, and we know it's going to get farther and farther and farther out. Similarly here, it went out to 8 at -π/12, and then goes way far out to infinity at -π/6. Well, what's happening here is it's a hyperbola, and those π/6, -π/6, and 7π/6 directions are the asymptote directions, and that's the directions in which it goes zooming out to infinity. Now, we only got one branch of a hyperbola, and that's because I wanted to avoid negative r's. If we allow negative r values, which I purposely skipped before, we can get both branches. It's kind of cool, but not something that's really crucial for us. So it turns out that basically any equation of this kind of form, where you have constant over constant plus or minus constant sine or cosine theta, those are how you get the conic sections in polar. And I'll do another real short video on the algebra of that, but this one's gotten long enough already.